In this section, we will use the Arduino Maker WAN 1300 to do a simple LoRa range test. You can however use any other end device as long as it sends uplink messages periodically. To follow along, you need the Arduino IDE installed along with the Arduino SAMD board definitions and the Maker WAN library. If you followed the LoRa WAN devices workshop this morning, you should already have these installed and have your Arduino delivering messages to the T10 console. We will do a quick recap. When you take the Arduino out of its box the first time and power it up, you will see the orange LED flashing, like you can see in the video down below. To get the Arduino talking to the Things network, we can follow the guide from the Arduino website, this one, how to connect Maker WAN 1300 and Maker WAN 1310 to the Things network. I'm going to do a quick demo of how I do these steps. So open the Arduino IDE, and I already have the libraries and the board definitions installed, which means under examples I will see the Maker WAN library and I choose first configuration. I verify this, and before I upload it, I open the serial monitor, and now I say upload. Okay, done uploading, and it starts with a welcome message. And now what we need to do is we need to use this EUI to register this device on the Things network. So I copy that and I open the console. I already created an application for my devices, and in this application I say add end device. The brand is Arduino. The model is the Maker WAN 1310 or 1300. The region I use is Europe. The frequency plan I use is the recommended one. The app EUI we don't have, so we choose this option for with zeros. The device EUI is the thing that I just copied from the serial monitor, so I paste this in here. And the app key I generate. Now the next step is to click on register end device. In my case, I already registered this device, so I'm not going to click there, but it will look the same as what we have here. So to complete the steps of the first configuration, we need to say 1 year because we're using OTAA. Then it asks us for the app EUI. App EUI is this value we copy here, and we paste it in there. And the app key is this one. I copy it here. And now because I know what's happening next, I'm going to go to live data in the meantime and clear here. And the value I paste it in there. And now we wait. And now the device is join a request. And we're just waiting for the first message. Message sent correctly. Now it should appear there. There we go. So this is the first message sent by our Arduino. We've got firstly the parsed payload, the JSON object. Our parser wasn't able to get the LED state out of it, so that's why it's null. Then we have the binary payload in hex here, followed by the port we used, which is 3. Then the data rate, so it used spreading factor 12, bandwidth 125 kilohertz, followed by the interesting part, which is the signal to noise ratio and the RSSI. So we've got an RSSI here of -89. That's quite good. And we've got a signal to noise ratio of 9.5, which is very, very good. Remember we said we expect the signal to noise ratio of between -10 and 10, and we expect an RSSI value of between -120 and -80. So these are both on the upper edge of the ranges we expect. If we click on this, we get to see more metadata here on the side. The interesting part is the RX metadata. The RX metadata is an array containing all the gateways that received our message. So in my case, I've got 1, 2, 3 gateways that received my uplink message. The first gateway received it at an RSSI of -89. That's the same values we see here. So the values we see here in the smaller form is only the first gateway's values. The second gateway received me at a slightly higher RSSI value and also a signal to noise ratio of quite high, a 9. The third gateway, however, we see an RSSI of minus 121, which is the lower limit that we would see, and a signal to noise ratio that is negative, and in this case it's quite negative. So this gateway, the last one, barely received us. And these two top gateways that received us were very well. So I've got two very good gateways here and a gateway that's not good, performing well. So this gateway, because both are negative, I assume this gateway is very far away. Just judging the signal from a single message is actually not good enough. So the next thing that I'm going to do is I'm going to change the Arduino code to keep on sending messages so that we have more messages to look at and to judge the signal from. So let me open the Arduino environment again. The sketch I'm starting with is the example to LoRa send and receive. So open this one up. By default, this sketch only sends messages when you press a button on your keyboard. So I'm going to change this. I already changed this, and you can copy the code from GitHub. If you go to this URL, I will provide a QR code for you to easily find this. So I copy all this code, which is just a modified version of the LoRa send receive. I copy this and I replace the entire code for the LoRa send receive here. So this code, if you look carefully here in the loop, it sends a message, begin packet, end packet. It delays 10 seconds and then it tries to send again forever and ever. So every 10 seconds we should see a message coming in on the Things Network console. Second thing to do is we need to paste in our keys here again. So I go back to the console. I copy my app EUI, paste in my app EUI, copy my app key, paste in my app key. I say verify. And I say upload. And while that's uploading, I'm going to go to the live data here and I'll just clear what we've seen here. And if all went well with upload, we should see a join, yes. And then any second now we should see an uplink message as well. Yes, there we go. And then 10 seconds later we should see another one. 4, 3, 2, 1. Yes, there we go. So every 10 seconds we should see an uplink message coming in here as well. If we go back to Arduino quickly and look at the serial monitor, what we see here is TX result equals 0 every 10 seconds. Sometimes the duty cycle limitations of the LoRa band doesn't allow us to send every 10 seconds, and then you will see different TX result here. But every 10 seconds with an empty frame or empty packet like we send here should work most of the time. So now what we can do is on the console we have multiple messages and we can keep an eye on the RSSI values here. So of course the order of the gateways we're not sure about, so we need to, in the case of multiple gateways like me, I need to open this again. And actually this is interesting, I only see 2 gateways here. 1 gateway, 2 gateways. The third gateway doesn't receive me this time. But we can easily now see the signal to noise ratio jumps around a bit. The RSSI value jumps around a bit. And now I have to confess something. I didn't plug in the antenna for my Arduino. This was on purpose, and I do not recommend you to do this. You should always have an antenna plugged into your Arduino because you can damage the hardware. So let me quickly plug in the antenna. Carefully. There we go. So it's the normal Arduino antenna I have here, this one. I'm just going to put it down there next to it on the empty cardboard box Arduino came in. And now, let's wait another 10 seconds and see what happens. There we go, TX result equals 0. And it was received. Yes, that's a big difference. So we jumped from an RSSI of minus 85 to an RSSI of minus 30. This is way too high. The poor gateway right next to me is being shouted at. And in this case, we might damage the gateway. But in this case, for my example here, this is very clear that plugging in an antenna is much better than not having an antenna plugged in. Another interesting thing to look at here is the number of gateways that received us. So we again back at 3 gateways, 1, 2, 3 gateways, and the gateway was that barely received us the previous time, that was at minus 121 the previous time, now is receiving us at a very strong signal of minus 69. This specific gateway is actually on my roof, so we've got metal roof tiles between the device and the gateway, and without an antenna the signal doesn't want to travel through those metal roof tiles. But with the antenna plugged in, we actually get the signal through, and it's going through quite well. I'm now going to unplug the Arduino from the computer, so the serial monitor will disconnect. I can close that now. I'm going to clear the log file here, and I have a USB power bank. I'm trying to show it to you here in this little video with a short USB cable on it, and I'm going to use this to power my Arduino. The reason I'm doing this is so that I can walk around with the Arduino. It's powered up again, and if all is well, yes, we see the join accept. And in a few seconds we should see our first uplink message. Yes, there we go. Signal to noise ratio 8.5, RSI minus 39, that's very high. So now with the Arduino being mobile, we can go and walk around and do a proper test. I have the console open on my mobile phone now, looking at the live data for the specific Arduino I'm using to do the test. You can see here, if you scroll sideways, you've got the signal to noise ratio and RSSI values here. It's not the best user interface for mobile, but at least we can see the SNR and RSSI while we walk around doing testing. Because Arduino is plugged into a USB power bank and my phone is running off of battery, I can take these 2 devices in my hands and walk around the block, and maybe walk as far as I can until I stop seeing messages arriving here. As I walk away, I should see the RSSI drop and the signal to noise ratio as well. And as I walk back, the RSSI should increase again and the signal to noise ratio should increase as well. So this is it's a usable solution to do LoRa range testing, but it's not ideal. In the next section we will do a demo of the TTM Mapper Android app that will help you make this much easier.